All right, Chapter 4, Probability. Probability is the numerical measurement of the likelihood that an event will occur. P of E right there, is equal to the probability of event E occurring. That's how you represent that, okay? The probability of an event is a fraction or decimal number between 0 and 1, inclusive. This is how you mathematically say that, okay? Probability of an impossible event, something that can't happen, is 0. Probability of an event that is certain, that absolutely 100% chance of happening, is a 1. Okay? Probabilities cannot be negative or 100. So the expression, I'm going to give it 110%, is not statistically correct. You can either be 100 or not. Okay? So it only, and it can't be negative. That makes no sense. Okay? And the sum of all the probabilities of the events that could happen is 100%. Okay? And the complement of an event is the probability that it will not occur. So here's how to say that mathematically. P of E equals 1 minus P of E bar, as in it won't happen, okay? And the opposite is true, right? So if you have one event and you want to know the event, 25% chance it's going to rain. Well, 100 minus 25 is 75% chance that it won't rain, okay? And then if you add the probability that it will rain and the probability it won't rain together, you get a 1 or 100%, okay? So this is what this is. This is the probability. The P of E is the probability that this will happen. Everything else that could happen is the probability it won't happen, which is the complement, or the E bar, okay? So here's a nice little scale. The scale of probabilities goes from 1 to 0, all inclusive, okay? 1 is uncertain, impossible is 0, 50-50 chance, 0.5, right? All these could be percentages. This is 100%, this is 0, this is 50%, right? Move the decimal place 2 places. Likely, unlikely, or in between there, okay? Believe it or not, probability of winning the lottery is way down to close to impossible, okay? Unfortunately, it's kind of in there somewhere, okay? Very, 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 very slim possibility. Probability, okay? So when we talk about probabilities, we want to talk about some more vocabulary here. The outcome, the result of a single trial of a statistical experiment. When you roll the die, that's a statistical experiment, okay? When you flip a card, when you pick a card, spin the spinner, what you get when you do that from that action is the outcome, okay? The sample space is a set of the entire, a set with set notation. It could be words, it could be numbers. Sample space is the set of all possible outcomes from picking a card, flipping a die. What possibly could happen? Okay, the event can be a single event that we're looking for. Basically, labeling one of our outcomes or a subset of the sample space. A single event is one outcome. So let's take, if I'm rolling a die, for example, okay, it's a 6-sided die. Since it's a 6-sided die, it's when I roll it, it's considered a statistical experiment. Sample space on this 6-sided die is the different outcomes that are possible. I could roll a 1 through 6, okay, could come up. Maybe the event I'm looking for is the die to be even. So that means 2, 4, and 6 would also qualify as the event happening. All right. Not a simple event is that even, odd number under 5, that kind of thing. A simple event would be as if I'm looking for a 2. Okay. The outcome is what I get. So I roll a die and I get a 3. That's the outcome. Okay. So you could have a probability experiment where you consist of tossing a coin and rolling a six-sided die. You could do it at the same time or you could do it after. It doesn't matter. We're just doing it once with the coin, once with the die. And when you toss a coin, there's only two possibilities, one head, or a tail, okay? But when you roll a die, there's 6 different possibilities. So if I'm doing both, whether it's at the same time or one after the other, my total different amounts of outcomes at the end, that coin is going to be sitting on one side and the die is going to be sitting on one side. And these are the 12 outcomes that I could get. I could get a head on the coin with a 1 on the die and so forth. Okay, so 2 possibilities on the coin, 6 possibilities on the die give me 12 outcomes possible. Okay, see how this is kind of like this here and then this here and then this here and then this here. That's considered a tree diagram. Okay, and these are its branches and its leaves at the end here with all the outcomes. For a tree, the tree could be representing a pick, a toss. Each branch is another tier, is another possible outcome from another something. So if we're rolling 2 die, it would be, 2 here, a 2 here, and it'd be 6 times 6 or 36 possibilities. Okay? So here's a spinner and a die. We're going to consider it a fair spinner, so it's equally likely to land on each number. All right, I don't know if the ones at the fairs are fair, right? But anyway, so if I'm tossing a coin, there's 2 possibilities. I'm spinning the spinner, there's 8 possibilities. So together there is 16 outcomes in my sample space here. Possible, okay? So what is the probability of tossing a tail and spinning an odd number? If you have all the possible outcomes written out, you can see that there's an odd number with a tail there, there, and there. So it's 4 out of the total 16 that we have. Okay? So you can reduce it as a fraction. You can put it as a decimal, 1 divided by 4. You can multiply that by 100 and get your 25% chance of tossing a tail and spinning an odd number. Okay? You can also think about it as the probability of tossing a tail is 1 out of the 2 choices. The probability of spinning an odd number is 4 out of the 8. Okay? And if you multiply them together, you're going to get 4 over 16. Okay? Let's multiply. So however you want to think about it. So look at the next one. Tossing a tail, 1 out of 2 chances. Spinning a specific 7 is only 1 out of the 8 different things that could happen with the spinner. If you multiply them together, you're going to get 1 over 16. If you look at your outcomes sample space here, you will find the 1 tail 7. That's the only thing the one event that would make that true. So it's 1 out of 16. Okay? Not spinning a 7, well, it's half for the tail. Not spinning a 7 is 7 out of 8, so 7 out of 16 is for that. Or you could look back up your outcomes. Tossing a tail and it not being would be T1, T2, T3, T4, T5, T6, T8. 1, 2, 3, 4, 5, 6, 7 possibilities out of a total of 16 possibilities. Okay, tossing a head and spinning less than a 6. Less than a 6. The sample space for less than a 6. 1, 2, 3, 4, 5. Okay, that's 5 different ones. 5 out of the 8 on the spinner. So 5 over 16. Or you could look up at the other. That's what? Head and less would be 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Identify the sample space using a tree diagram of tossing 3. Okay, coins. So H, let me see if I can fit this on here. T, that would be the first toss. Possibilities. Okay, and then from there, you're going to toss another coin. That's the second toss. And from there, you're going to toss another coin. So it could be the same coin 3 times, or it could be 3 different fair coins that are the same, and do it at one time. The possibilities that you're going to get are 2 times 2 times 2, or 8 different outcomes. 1, 2, 3, 4, 5, 6, 7, 8. All right, the way you label these, this is HHH is one outcome, right? HHT is another. HTH, HTT, THH, THT, TTH, and TTT. Now, if I did that right, I should have 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Think of these as 3 physical coins. Okay? So the order is important when you're writing that out as far as what you could have. Okay? Given that the first one was an H, the second was an H, or given that the first was an H and the second was a T, then the third one was an H. So it does follow this kind of tree for a flow chart, kind of, to see what you got. But that gives you your 8 different outcomes. Okay?